Okay, so next section 2.7. So in this section we are going to study group homomorphisms. A homomorphism in general is a mapping from one algebraic system to a like algebraic system that preserves structure, algebraic structure. So for groups, let us see what the definition is. A homomorphism phi from a group G to a group G prime is a mapping phi from G to G prime such that phi of AB is equal to phi of A, phi of B for all A and B in G. Okay, so that's what a homomorphism from one group to another group is. So we can see the situation using an arrow diagram for the function. So say this is G, this is G prime. These are the two groups. Now what this thing says is that if we take two elements A and any two elements A and B in G and we form their product AB in G using the binary operation that we have in G, and then on that we apply the map phi to get phi of AB, and if we individually apply the map phi on A and B, getting the images phi A and phi B, then the product of these two elements in G bar using the binary operation in G bar is actually equal to this image. So preservation of structure, so this is the map phi. Preservation of group structure here in this sense is this. You are doing a calculation in the first group, the domain group. You are calculating the product AB. Okay. Instead of looking at the calculation directly, you can look at the image of the calculation under phi. So phi is like a mirror. In front of the mirror you have one group and its mirror image lies on the other side of the mirror. So whatever you are doing in this group, the mirror, in the mirror world, a similar thing will happen, which is not exactly the same thing but a similar thing which mimics what is happening here on this side. So here instead of the elements A and B, we have the images phi A and phi B respectively. Now if we calculate the product phi A, phi B, so it's like calculating the product AB, except in here we are calculating such a product in the other group. Then the product gives us something. That something is equal to the mirror image of AB. So it's like doing something here and then looking at the mirror image of the result, that gives you the same result as first looking at the mirror images and doing that corresponding thing with the images. So in that sense the structure is preserved. And in fact from this interpretation we can see one thing, that in this equation, although we are not because we are using multiplicative notation in which we have decided to not use any symbol for the binary operation and write the product of A and B simply as AB. So it may not be apparent in the beginning itself what the equation hides. Since AB is the product that has to be computed in G, so here we have used the binary operation in G. But since phi A phi B is a product of two elements in G bar, here the operation is that of G bar. In fact, that is the remark that comes after this definition. Notice that on the left hand side, on the left side of this equation, this equation means the equation that we have in the definition, namely in the term phi AB, the product AB is computed in G. Using the product of elements in G. Whereas on the right side, the product, or we can write just like above, namely in the term phi A phi B, the product is the one in G bar. Okay, but although we have not denoted these products using different symbols, but it should be clear from the equation itself, because A and B are elements in G, so to calculate the product AB we will use the operation or the product in G. And because phi A and phi B are elements in G bar, so there the product in G bar will be used for the computation of this. Okay, now we'll look at some examples of homomorphisms. Example 2. Oh, Herstein has started the examples from, I think he starts from 0 always. Let G be any group the mapping phi from G to G, we can take both the groups to be the same group. There is no restriction that the second group has to be different from the first one. G to G defined by phi of G equal to G is a homomorphism. So that means here phi is the identity map on G. This is because for any A and B belonging to G, we have phi of AB. I need some ink first. So by definition phi of AB is just simply AB, but again by the definition of phi, A is phi of A and B is phi of B. So in a somewhat trivial manner, the identity map on any group is a homomorphism. Next, in this same example, let G and G bar be any groups define phi from G to G bar. We should understand that this phi is not equal to this phi, okay? We may use the same name, but the function each time is likely something else. I mean something different from the previous situation. So define this by phi of G equal to E bar, where E bar is the identity element in G bar. Then for all A and B belonging to G, we have phi of AB is equal to, by the definition this is equal to E bar, but in G bar, E bar can be written as E bar, E bar, and again using the definition of phi, this is phi of A and this one is phi of B. So in this second example, I mean in the example 0 itself, in this second function, the function is actually a constant function. At every element in the domain group, the value is constantly the identity element in the second group. So for this function also, in a trivial, somewhat trivial manner, the function is proved to be a homomorphism. Then a slightly more non-trivial example. You can have, in place of these two groups, you can have the same group also. In that case, all the elements of the first group will be mapped onto the identity element of that group itself. Let G be the group of all real numbers under addition. Addition, and let G bar be the group of all non-zero real numbers. Under multiplication. We already know that these systems are both groups. Define phi from G to G bar by this formula. Phi of A is defined to be equal to 2 to the power A. Okay, so A is any real number, and 2 to the power A of course is a real number, and we already know that 2 to the power A is a non-zero real number. A power like this can never be equal to 0, okay, from properties of real numbers. Specifically, it follows. So that means this function is well defined. We should not forget that every time we are defining some function, we have to first of all make sure that the function is well defined. So for these things, the situation was quite easy. For this, however, here also the situation is easy. The thing is that you have to make sure that every element in the first group has a unique image. Now every element does have an image. Whether that image belongs to the second group, yes, it does, because this power can never be equal to 0. So all the images are non-zero real numbers, and for a given real number this power is of course unique. So the function is well defined. Additionally, the function is a homomorphism. So it follows from proposition 673 of analysis 1 by Terence Stock. We are referring to those results because this is a fact about real numbers. The thing here is that we are simply using one of the rules of exponent that are true for real numbers. Phi is a homomorphism for A and B belonging to G. We have phi of A plus B. Note that here we are actually using the binary operation that we have in G, because G is the additive group of all real numbers. So the operation is addition. The image is 2 to the power a plus b, and this is where we use this rule of exponents, and this is phi of a and this is phi of b, and the operation here is actually multiplication of real numbers. So here we have addition, there we have multiplication, so the structure is preserved. Okay. In fact, we can write something else here. Let's just write like this. This same result, that is this proposition 673, from tau also shows that phi of a equal to 2 to the power a is greater than 0 for all a belonging to G. Not only are powers like this always non-zero, but in fact they are all positive. Thus, phi as a function is not onto, it's not a surjective function. That is because in the second group of all non-zero real numbers, we do have negative real numbers. Those will never occur as the image of something from G under the function phi. So that's why phi is not onto. Okay. Then let G be equal to S3, the symmetric group of degree 3, whose elements we already know: E, phi, psi, psi square, phi psi and psi phi. Or if we want, we can write the element psi phi as phi psi square, same thing. And let G bar be the subgroup of S3, cyclic subgroup generated by phi. So let these be the two groups we will use to construct a homomorphism. Define a mapping phi from G to G bar by defining like this. Phi, we already, okay, we cannot use phi because phi is already an element here. So let's use something else. Let's call this f. F of phi to the power I, psi to the power j equal to phi to the power I. So this is our definition of the mapping f. Now we do have to verify that this f is well defined. First of all, let us see whether the f makes sense or not. We are saying that any element in S3 which looks like this will be mapped onto this element. Now the point is, are the elements of S3 always of this form? Yes, they are. Let's see the elements one by one. E can be written as phi to the power 0 psi to the power 0. Phi is phi to the power 1 psi to the power 0. Psi of course is phi to the power 0 psi to the power 1. Then this element is psi square. This one of course is phi 1 psi 1, and this one is phi 1 psi 2. Okay, so all elements really are of this form. So fine. So we can in fact take the general input to the function f like this. And what is the output? The output is phi to the power I. Now we have to make sure that this output is unique. And one more thing, the output really is in G bar in all the cases, because G bar is a subgroup and this is an integral power of the element phi. So whatever I is, it's either going to be E or phi. It will be trapped in the subgroup itself by closure property. But that uniqueness we have to show. Note that every element of G is of the form phi to the power I psi to the power j and phi to the power I belongs to G bar for any integer I. Okay. Now let I, j, k and l be integers such that these two elements are equal. Okay, then we can use the group axioms to have this. Then, and using the rules of exponent, phi to the power I minus k is equal to, we should be careful how we are achieving this one. Let me just first write the equation L minus J. How do we get this equation from this one? We should be careful because the group we are dealing with is non-abelian. So we cannot just simply multiply both sides by say phi to the power minus k. From which side we are multiplying, that also matters. So we multiply on both sides by phi to the power minus k from the left. So on this side we will have phi to the power I minus k times psi to the power j, and on this side we will have phi to the power k minus k times psi to the power l. That means we will have this. So the right hand side becomes psi to the power L. Now you multiply both sides from the right by psi to the power minus j. That will give us this. Okay. But this implies what? Which implies that phi to the power I minus k belongs to the cyclic subgroup of S3 generated by psi, which is equal to E psi square. Because after all this is an integral power of psi, so it will belong to the cyclic subgroup generated by psi. Now what can this integral power be? Since it belongs to G bar, this integral power, whatever I and k are, is either E or phi. That means it's either phi to the power 0 or phi to the power 1. Phi to the power 0 is E, phi to the power 1 is phi. Now note that phi itself does not belong to this. So that means this has to be equal to E. Okay, this has to be equal to E, and so actually, okay, let me just put this simply. Either this is equal to E or this is equal to phi, but it cannot be equal to phi because phi does not belong to this set. So that means it has to be equal to E. Since belongs to E comma phi and phi does not belong to the cyclic subgroup generated by psi, we must have phi to the power I minus k equal to E, or using the rules of exponent again, phi to the power I equal to phi to the power k. Hence f of this is equal to phi to the power I, which is equal to phi to the power k, and that is equal to f of psi to the power L. So this shows that if two elements in S3 or in G, same thing, are equal, then their images are also equal. Thus F is well defined. So well definedness of F here is not trivial or not something that can be seen immediately. Okay, you have to put a little effort to show this. Now comes the question of showing that F is actually a homomorphism. For that you note this. Now from this relation which is true in S3, psi phi equal to phi psi square, one can show that this thing holds. That if we take the product of these two elements, say phi to the power I psi to the power j and phi to the power k psi to the power l, then that equals this. phi to the power I plus k psi to the power j plus L if k is congruent to 0 mod 2 and it is equal to phi to the power I plus k times psi to the power 2j plus L if k is congruent to 1 mod 2. Exactly how one gets this result, I am not going to say anything about that. I leave it to you to figure out. You can use this relation to make sense of this result. Okay. So both the cases we have covered. What happens when k is even and what happens when k is odd? You just have to take an even value of k and an odd value of k and apply this relation to calculate such a product. And remember one more thing, although here it looks like I and k are any integers, but after all everything depends on the parities of I and k. If I is even, then phi to the power I is the identity E, and if I is odd, then phi to the power I is equal to phi. So these are the only two possibilities. So that means the first element, for example, is either only psi to the power j or phi times psi to the power j. That's it. And we need the form of this product because we should be able to apply f on this product to see what the f image is. Thus, or so, if we now apply f on this product, then this is either equal to this or this. So by the definition of k, whatever be the case, it's always equal to phi to the power I plus k. Then apply the rule of exponent to write it like this, and this is f of phi to the power I psi to the power j, and this one is f of phi to the power k psi to the power L. So this shows that f is actually a homomorphism. And perhaps I should make one more thing clear. Here we have assumed I, j, k and L to be integers for which these two elements are equal. Here they are not restricted like that. Here I, j, k and L are general integers. In fact, I think it will be better to not use these symbols and use something else. Let me use alpha, beta, gamma, delta. Alpha plus gamma, beta plus delta, where in this context you should understand that alpha, beta, gamma and delta are integers, any integers. Beta is congruent to 0 mod 2, beta is congruent to 0 mod 1. Alpha plus gamma, 2 beta plus delta. So this is a homomorphism. Example 273. So this was 2. Let G be the group of integers under addition and G bar be equal to G itself. Define phi from G to G bar by this formula. Phi of x is equal to 2x. So we are just taking the double of an integer, which again is an integer, and this function is clearly well defined. And this one is rather easy. For any two integers x and y, we have, because the binary operation is addition, so we write like that, x plus y. This is equal to 2 times x plus y. Then use the fact that multiplication of integers distributes over addition of integers. So write this as 2x plus 2y, and this is phi of x plus phi of y. So here, since both the groups are additive, I mean in fact the same group, so the operation is addition. Thus phi is a homomorphism, and since we have odd integers, so this homomorphism is not onto, because the images are all even. Then example 4. Let G be the group of all non-zero. Okay. Let non-zero real numbers under multiplication. And let G bar be the set consisting of the real numbers -1 and 1 under, again, ordinary multiplication. It's easy to see that G bar is, it forms a group under multiplication. Define phi from G to G bar by this formula. Phi of x is defined to be equal to 1 if x is positive and -1 if x is negative. This I leave to you, this verification. Verify that phi is a homomorphism from G onto G bar. this one is onto. In fact, the the statement that phi is a homomorphism is just simply another way of saying that product of two positive real numbers is positive, a product of two negative real numbers is positive, and a product of a positive and a negative real number is negative. So it's because of these facts phi is a homomorphism, and conversely, because phi is a homomorphism, these facts are true. The function also makes sense because G has only non-zero real numbers. So any x you choose from G, it's either going to be positive or negative by trichotomy of real numbers. Okay, then example 5. Let G be the group of integers under addition. And G bar be the group of integers modulo n. Under, oh sorry, not multiplication, addition modulo n. Define phi from G to G bar by this formula. Phi of m, where m is some integer, is equal to the congruence class R modulo n, where R is the remainder we obtain when we divide m by n, and this is the congruence class modulo n containing R. Okay, so let's see that this function is now well defined. We choose any integer m from the additive group of integers. If we divide m by n, then we will get, first of all, we will get an integer, that is the remainder, and that remainder is unique. from the division algorithm or from the Euclidean algorithm. So if we then consider the congruence class containing that remainder, then because distinct congruence classes modulo n are disjoint, so there exists a unique congruence class that contains the remainder. So this congruence class is unique, and there is one congruence class where the remainder is a member. That's because if we take the union of all the congruence classes modulo n, we are going to get the set of integers back, and that is because the congruence classes modulo n form a partition of the set of integers. So the function is well defined. Instead of saying all these things, it's clear that phi is well defined. Okay. Now we have to verify that phi is a homomorphism. So let m1 and m2 be any two integers. Let r1 and r2 be the remainders we obtain when we divide m1 and m2 by n. Respectively. Okay. If R3 is the remainder on division of R1 plus R2 by n, then let's do the calculation here. This time let's start from the other side. Phi of m1 plus phi of m2. So r1 is the remainder when we divide m1 by n, so this is equal to the congruence class r1 containing r1, and this is the congruence class containing r2. And by the definition of addition, okay, one more thing, note carefully that because we are adding two elements in G bar, which is the group of integers modulo n under addition modulo n, so this plus is addition modulo n. So according to the definition of addition modulo n, this is equal to this congruence class, and since the remainder obtained when we divide r1 plus r2 by n is r3, so this congruence class is the same as r3. Okay. Now we want to claim that this congruence class is actually equal to the phi of m1 plus m2. That's what we want. Okay, so we want to claim that this congruence class is equal to m1 plus m2. Let us just directly write that and then we will justify. Note that since M1 is congruent to R1 mod n, M2 is congruent to R2 mod n, do we really need to consider R3? That's what I am thinking. No, there is no real need to consider R3. We can start the calculation from here itself. Then this is equal to this one is equal to this by the definition of phi, and by the definition of addition modulo n, this is equal to this. And now our claim is directly this. Since we have this and this, it follows that from properties of ordinary congruences, M1 plus M2 is congruent to R1 plus R2 mod n, and hence the corresponding congruence classes are equal. And that's why we have the equality here. Thus, phi is a homomorphism of G to G bar. Clearly, phi is onto. Why is that so? It's because if you choose the actual congruence classes in G bar, which are these 0, 1, 2, etc. up to n minus 1, then this is nothing but phi of 0, this is phi of 1, this is phi of 2, like this, and this is phi of n minus 1. All these integers are less than n and non-negative. So if any one of them is divided by n, the remainder is the integer itself that is being divided. So that's why phi of 0 is equal to this, phi of 1 equal to this, and so on. Note one more thing, that the domain group here is infinite. It's the additive group of all integers. But the second group is finite. It has only n elements. So we can have a homomorphism from a finite group, from an infinite group to a finite group. We can have it the other way also. However, that is not so. That does not tell us anything much about the situation. You will understand what these things mean. We can have a homomorphism from a finite group into an infinite group. It does say something else, but this one is an observation. Then there are two more examples, and after that we will move to the results. Let G be the group of all positive real numbers under multiplication. This is a group we already know, or it can be easily verified. And G bar be the group of all real numbers under addition. So here we have the first group is multiplicative and the second group is additive. Define phi from G to G bar by this formula. Phi of x is defined to be equal to log x to the base 10. Note first of all that the function makes sense. It's because we are taking the logarithm of a positive real number which exists. And since the function is nothing but the logarithmic function to the base 10, so it's well defined also, because it's a known well defined function in analysis. Then for any two positive real numbers x and y, we have phi of xy. Now the first group is multiplicative, so we are using multiplication as binary operation here. So this is log xy to the base 10. Now use properties of ordinary logarithm plus log y to the base 10. So this is equal to phi of x plus phi of y. So algebraic structure is indeed, group structure is indeed preserved. Thus, phi is a homomorphism. Also, from properties of logarithm, phi is onto. The function phi actually is onto, which is a function from the set of all positive real numbers into the set of all real numbers. We already know from properties of logarithms that such a function is onto. Its inverse, however, which is the function 10 to the power x, it's a function like this. That's why we say when we take powers, we get not only non-zero real numbers but positive real numbers. This one is also onto, that one is also onto. In fact, it's both bijective, one-to-one and onto. That's why the inverse functions exist to each one of them. When we study logarithmic functions, exponential functions in not in analysis 1 by Terence Tao, but in analysis 2, there we will actually prove these things, that these are onto functions, they are bijective, if we restrict the domain and range properly. So those things we will prove there. And finally, this example is, it has a hash tag. That means it needs knowledge of matrices. Let G be the group of all 2 by 2 real matrices. Two by two real matrices A, B, C, D, such that the determinant AD minus BC is not equal to 0. Although in this book we haven't yet got the concept of determinants, at one point we will get, but there is quite some time before we get to that point. But still, since you already know about matrices, determinants and things like that, so I am just calling this the determinant of this matrix. So the determinant is non-zero under matrix multiplication. So this is our first group, and let G bar be the group of non-zero real numbers under multiplication. Define phi from G to G bar by this formula. So here the function has matrix inputs and the outputs are their determinants, which is a real number. Now, because we are considering non-singular matrices, where that is matrices whose determinants are non-zero, so the images are all non-zero real numbers, so the images all actually lie in G bar, and this clearly is a well-defined function. In fact, the name of this function is the determinant. If you really look at what determinant of a matrix means, that definition uses determinant as a function. Although we say that AD minus BC is the determinant of this matrix, but truly determinant means the function that gives the value of the determinant for a given matrix. So this function is called the determinant. It's the value of this determinant. Okay, now it's well defined. Clearly, phi is well defined. Now it's a fact that the determinant function in this sense is a homomorphism, but let's just show that for this, because the order here is quite small, 2 by 2 matrices. Now let A, B, C, D and EFGH be two matrices in G, then phi of A, B, C, D times EFGH is equal to phi of AE plus BG, AF plus BH, CE plus DG, CF plus DH. This is equal to AE plus BG times CF plus DH minus AF plus BH times CE plus DG. So let's multiply the terms out. AECF plus AEDH plus BGCF plus BGDH minus AFCE minus AFDG minus BHCE minus BHDG. So we have cancellations AECF minus AECF. So these two terms cancel each other. Like that, BGDH, BGDH, plus and minus. Okay, now AD minus BC we need. So from this term EH and this term, let's take EH common out from these two terms. Then we have AD minus BC EH, and we are left with, of course, this term and this term. From these two we are going to take minus FG common out. So if we take minus FG common out from the first one, then we have AD, and from BGCF if we take minus FG common out, then we will have minus BC. So this equals AD minus BC times EH minus FG, and you can see that this is the determinant of the first matrix and this is that of the second matrix. I think now I am remembering that we have done this calculation before, in fact showing that G is a group when we studied examples of groups. Anyway, it does not hurt to repeat it for once. Hence, phi is a homomorphism. Is phi onto? I leave that query to you. You try to see whether phi is onto or not, and if so, try to prove it. Okay, let's now look at some results. So we have seen quite a few examples. Let's now look at some general properties of homomorphisms. And the first result gives us a way of creating homomorphisms if we are given normal subgroups. So this result and some others that are coming will show us that homomorphisms of between groups and normal subgroups are actually intimately related. If one is given, then you will get a corresponding, say for example, if you are given a group and you are given a normal subgroup of the group, then using these two things you can create a homomorphism from that group to some other group. Conversely, if you are given a homomorphism from one group to another group, then you will find a normal subgroup of the domain group that is somehow related to that homomorphism. So let's see the first result. Let G be a group and N be a normal subgroup of G. Then the mapping phi from G to the quotient group, because N is a normal subgroup, we can form the quotient group G by N. Given by phi of G equal to the coset Ng is a homomorphism of G onto G by N. That part is also true, it's an onto a surjective homomorphism. Proof is very simple, but the fact is important. For any, before we show that phi is onto, phi is a homomorphism, let's just notice that phi is clearly it's onto, obviously, because if you consider any element here in the quotient group G by N, it's after all going to be some coset of N. So the coset will have a representation like this. So it will be the phi image of G, of that element which appears in that representation. So we start the proof by noting this fact. Obviously, phi is onto. Next, for any elements x and y belonging to G, we have phi of xy equal to nxy, and since n is a normal subgroup, we have already seen that this equals nx ny. In fact, we know why this happens. n nxy can be written as nnxy. N is equal to nn because n is a subgroup of G. Then we use the associative law to combine n and x together and write the set like this. Then use the fact that n is a normal subgroup. So nx, this right coset will be equal to this left coset, and this is just equal to this. Okay, so this simply is phi of x, phi of y. So that's just it, it's that simple. So this allows us to create homomorphisms of groups. What you have to do, you take a group and find normal subgroups of the group, and then you form these quotients and immediately you have homomorphisms. For each normal subgroup you will have a homomorphism. Okay, now when we were looking at these examples of homomorphisms, we tried to see whether the homomorphisms are onto or not. But at the same time, there is one more aspect also related to onto-ness, that is one-to-oneness. And not all the homomorphisms are one-to-one. In fact, some of them are not one-to-one. For example, if you look at a group G which has more than one element, it has something other than the identity, then you consider the map from the group to itself where all the elements are mapped onto the identity. Then this map or this homomorphism is clearly, this one we saw in example 270, is clearly not one-to-one. It is a many-to-one function. However, the other homomorphism we saw in that same example, which shows that the identity map is a homomorphism, that definitely is one-to-one. Okay, so like that, every homomorphism is either one-to-one or not one-to-one. Now, unlike ordinary mappings between sets, whenever a homomorphism is not one-to-one, its deviation from one-to-oneness is somewhat uniform. And to see what that means, we need a new definition. Let G, G bar be groups and phi from G to G bar be a homomorphism. The kernel of phi denoted by k suffix phi. We are going to use this notation in this book. Okay, whenever the phi is a group homomorphism, and then its kernel is going to be denoted by k suffix phi, is the subset k phi equal to the set of all elements in G such that phi of G is equal to E bar. The identity element in G bar. Okay, so that means the kernel of a homomorphism, not kernel of a group, okay, kernel is of a homomorphism by definition. A homomorphism has a kernel, is defined to be the set of those elements in the domain group that are all mapped onto the identity element of the second group. This is K phi. So you looking at the two mappings here in example 270, we see two extreme cases. For this map, the first one, not the first one actually, the second one, the kernel is the entire group G. Note that according to this definition, the kernel K phi is actually a subset of G because the elements in it are coming from G that satisfies something else, some condition. Okay, so this is a subset of G in general. For this second mapping, that subset, that is kernel of this particular map, is the entire group because all the elements are mapped onto the identity element. However, for this other mapping, namely the identity map, the kernel is not the entire group. In fact, it consists of only the identity element in G. Why that is the case, that we will see. So in this first case, the kernel is as small as it can possibly be, and in this case the kernel is as big as it can be. In between also we have kernels. Now the next lemma tells us two very important things about a homomorphism, and this will in turn tell us something about the kernel of a homomorphism. These subsets are going to be important in what we are going to do now. So let's see the next lemma. Let G comma G bar be two groups and let phi from G to G bar be a homomorphism. Then the following two things are true. Then number one, phi of E is equal to E bar. The identity element in G bar. And number two, phi of X inverse is equal to phi of X inverse for all X belonging to G. What it means is this. Say we have a homomorphism from group G to group G bar. Then if one applies the homomorphism to the identity element of G, then one will always get the identity element of the second group. That is the first thing. And the second thing is that if we take any element from the domain group X and take the phi image of the inverse of X, phi of X inverse, then that is the same thing as the inverse of the image phi X in G bar. Okay. So let's see the proof. We have phi of E equal to, since E is the identity in G, so it can be written as EE. And because phi is a homomorphism, so phi of EE will be equal to phi of E, phi of E. That is, E bar phi of E is equal to phi of E, that is equal to phi of E, phi of E. Now look at this equation. E bar phi of E, of course, is phi of E because E bar is the identity element in G bar. And this we have seen because due to the fact that phi is a homomorphism is equal to this product. Now this is an equation in the second group G bar, where we have phi of E on both sides to the right of these elements. So we can cancel phi of E from both sides using the right cancellation law that we have in the second group. So by the right cancellation law in G bar, we have E bar equal to phi of E. So that's what we had wanted to show. So this proves part 1. For part 2, we start with this thing. After choosing one element X, of course, let X be any element in G. Then by part 1, phi of X inverse phi of X. Let's start the calculation with this product. Since phi is a homomorphism, this is going to be equal to phi of X inverse X, but in the group G, X inverse X is E. So this is phi of E. Now this is where we use part 1. Phi of E is equal to E bar. And E bar can be written as phi X inverse phi X. That is the inverse of the element phi X in G bar times phi X. Thus, again here we can cancel. We have again an equation in the second group G bar where we have phi X on both sides, which we can cancel. Thus by the right cancellation law in G bar, we have phi of X inverse equal to phi X inverse. So this completes the proof of this lemma. Now what does this lemma have to do with kernels of homomorphisms? Look at part 1. If you look at the definition of kernel, then say you have G and G bar, there is a homomorphism phi, and the kernel by definition is actually nothing but this, the inverse image of the element E, precisely those elements in G whose images under phi are equal to E bar. Now had phi been any arbitrary mapping, there is no guarantee that this inverse image will have something in it. It will have something provided E bar belongs to the image set of the function phi. If it lies outside of the image set, then clearly it has no pre-image. But the beautiful thing here is this: if it's a homomorphism and the sets are groups, then it has at least one pre-image, and that pre-image is E. Okay, so you know that whatever be the case, at least E is here. The identity of the first group always lies in the kernel of the homomorphism, because it always gets mapped to the identity of the second group. So from this fact, we know that the kernel is always non-empty. It's never empty for any homomorphism. So we are now going to mention that fact. But before we say that, let's interpret these results in a familiar situation. Let G be the group of all positive real numbers under multiplication, and G bar be the group of all real numbers under addition. Let phi from G to G bar be the mapping that we have already seen in the examples that we considered in this video. That is the logarithm function, such that phi of x is equal to log x. We have already seen that phi is a homomorphism. Okay, we have seen this. So that means we can apply this the result of this lemma 272 to this particular homomorphism. What do we get when we apply it? If we apply phi to the identity of the first group. The first group is the multiplicative group of all positive real numbers. So there the identity element is 1. Then we should get the identity element of the second group, which is the additive group of real numbers. So the identity is 0. Is it true? Phi of 1 is log 1, and we have seen if in schools when we came across development of logarithms to the base 10 or to any such base, there we have already proved that log 1 is 0. Also, if we take any element in the first group, that is any positive real number, say x is a positive real number, then log 1 by x, 1 over x, is nothing but phi of x inverse. X inverse in this first group is the reciprocal of x, because the binary operation is multiplication. So phi of x inverse, this should be equal to phi of x whole inverse. That means the inverse of phi of x, that phi of x is log x, but in the additive group of real numbers. So that means minus log x. This formula also we came across in our previous experience with logarithms. If we remove reciprocal, then we have to put a minus sign here. Or if you don't remember this one, then think of x to the power minus 1, log of x to the power minus 1, that exponent comes and gets multiplied with the logarithm. So that means these facts that we already know are special cases of this general result about groups. Okay, now we come to this observation. We have seen that if phi is any homomorphism, then the kernel is always non-empty. In fact, much more can be said about the kernel. Namely, the kernel is not only a non-empty subset of the domain group, but it's in fact a subgroup, and that too a normal subgroup of G. So that is the next lemma. Let G comma G bar be two groups and phi from G to G bar be a homomorphism. Then the kernel of phi, k phi, is a normal subgroup of G. So do you see the other side of the coin now? In that lemma where we had a group and a normal subgroup, using these two things we created a homomorphism from G onto G by n. Here, however, we are given a homomorphism, then because from that homomorphism we are getting a normal subgroup. Okay, so the two things are related, the concept of a normal subgroup and a homomorphism. by part 1 of Lemma 272, E belongs to the kernel of phi. So it's a non-empty subset of G. So this is a non-empty subset of G. Now we have to first of all prove that K phi is a subgroup, and then we will show that it's a normal subgroup. Now let X and Y be two elements in K phi. Then, being elements in the kernel of a homomorphism, if we apply the homomorphism on these elements, we are going to get the identity element of the second group. Then phi of X is equal to E bar and phi of Y is also equal to E bar, where E bar is of course the identity of the second group. We have said it quite a few times, so we are not mentioning it once more. In the context it's clear. So what about we do need the second part of this lemma also. So by part 2 of Lemma 272, phi of X Y inverse, this is equal to, because phi is after all a homomorphism, so this is equal to phi of X, phi of Y inverse. But by part 2 of this lemma, phi of Y inverse is phi Y whole inverse. So this is E bar times E bar inverse, which is equal to E bar. So looking at this final equation, we see that the phi image of XY inverse is also the identity element of the second group. So that's why XY inverse also must belong to the kernel of phi. This implies hence K phi is a subgroup of G. Now the only thing we are left to show is that K phi is a normal subgroup of G. Next, let G be any element of G and N be any element in K phi. Then our aim is to show that G and G inverse is again an element in K phi, which means that we have to show that if we apply phi on G and G inverse, then the result is the identity element of G bar. So that means let's calculate this. This is equal to phi of G, phi of N, phi of G inverse, using the fact that phi is a homomorphism. But now the first one of course is phi of G. The second one is the identity element in G bar because N belongs to the kernel. and the third one again by part 2 of lemma 272 this, and this is equal to phi of g inverse. This means g and g inverse belongs to k phi. Hence, k phi is a normal subgroup of G. That's what we claimed. So this completes the proof of the third lemma. And finally, let's just do one more result and then we will call it a night. If phi is a homomorphism from group G into group so this is onto group G bar with kernel K, then the set of all the inverse images of some element G bar belonging to G bar under phi in G is the right coset Kx, where X is any particular inverse image of G bar under phi. So this result says something about the kernel. So here we have a homomorphism phi from G onto G bar. Okay, so onto means the function is surjective. So if we take any element G bar belonging to G bar, it has at least one inverse image, and the inverse image is clearly, it's denoted by this. It's the set of precisely those elements in G whose images under phi are equal to G bar. So there is some inverse image, say X. This X belongs to phi inverse of G bar. Then this phi inverse of G bar actually is equal to the coset of the kernel given by X. Because we have already proved in the previous lemma that the kernel is a subgroup, so coset makes sense, and this coset is the collection of all the inverse images of G bar under phi. So let's prove this. It's quite easy actually. We have phi of x equal to G bar. Let k be any element in the kernel K. Then Kx belongs to G such that phi of Kx is equal to, since phi is the homomorphism, this is phi of K times phi of X, but since K belongs to the kernel of phi, so this is going to be the identity element of the second group, and phi of X is equal to G bar, so we get G bar. So this proves that Kx is an inverse image of G bar, or Kx belongs to the set of all inverse images of G bar. This is the claim, okay. This implies Kx belongs to phi inverse of G bar. But Kx, according to the definition of a right coset, is any arbitrary element of this right coset. Thus, Kx is a subset of phi inverse of G bar. Conversely, let y belong to phi inverse of G bar. Then phi of y is equal to G bar. That is the definition of being in the inverse image of G bar. Since phi is onto, so this is where we use the fact that the map is onto. G bar is equal to phi of h for some h belonging to G. Okay. Thus, phi of y is equal to G bar. This is equal to phi of h. Now, what happens if we calculate phi of h inverse y? H inverse y is an element of G. What is its phi image? Let's see. Phi of h inverse phi of y. since phi is a homomorphism by part 2 of lemma 272, this is inverse phi of y. But we have already seen that these two things are equal, so that means this is phi of y inverse phi of y, and this is equal to E bar. This implies H inverse y. Oh, we have taken H inverse y. No, I think this one will help us instead. Y H inverse. So we just have to change all the things accordingly. Phi of y, phi of H inverse. So this is phi of y inverse, same result, but the order is different. So YH inverse belongs to the kernel of phi. Hence, y can be written as this. Y is equal to YH inverse H. Oh, okay, wait. I think there is no need to consider H, because how foolishly I considered H. I already have an H, which is X. Okay, let me modify this part. Sorry about these mistakes, but the thing has to be proper. Now, since G bar is equal to phi of x, it is given that x is a particular inverse image of G bar. That means phi of x is equal to G bar. So we have phi of y is equal to phi of x. Now yx inverse belongs to G such that phi of yx inverse is equal to phi of y, phi of x inverse. Now phi of y is equal to phi of x, and phi of x inverse by part 2 of lemma 272 is equal to the inverse of phi of x. This is equal to E bar. This implies that this element yx inverse belongs to K. Hence, the element y, which can be written as yx inverse times x, this must belong to kx, because this part belongs to k, so it belongs to the coset kx. So here we have shown that any element y in this inverse image also belongs to the right coset. Thus, phi inverse of G bar is contained in kx. We now combine these two inclusions. and conclude the proof. So we finally have phi inverse G bar equal to Kx. This particular result has an application in the theory of linear differential equations, ordinary linear differential equations. Let me just briefly say what that application is. You know that an ordinary linear differential equation looks like this. Oh, I think it's better to write like this, and here you have some function of x. Now these ai's are differentiable or continuous. You can take continuous functions of x. Bx is also a given function of x. These are all known. Y is an unknown function of x. Now you can view this differential equation as an operator equation where you are operating on the unknown function y by a linear differential operator. That operator in this case is this. This is the operator where I denotes the identity operator that takes the function y and gives back y. Okay, so applying this operator on y is the same as applying these individually on y and then take their sum. In fact, these additions, multiplications, these are all defined in the space of operators. Okay, so those things are there. So the point here is that the space of all solutions or the set of all solutions to this differential equation, it forms a vector space. Although we haven't seen vector spaces yet, but I'm just saying, if you know about vector spaces, then because the differential equation is linear, the space of solutions forms a vector space, and this vector space is a group under addition, and the fact that this is a linear differential operator tells us that this is a homomorphism also on this group, okay, on this additive group of solution space. Now, in place of this Bx, which is a known function, you can consider that G bar there in this result. Y is a pre-image of G bar. Now, if you are able to find a particular integral, a particular solution to the differential equation, that means say you have found a particular integral which is some solution to this differential equation, and you are able to find all the solutions to the corresponding homogeneous equation where this 0 is the zero function that gives you the value 0 at every real number or at every point in the domain where the differential equation is defined, then the solutions to this homogeneous equation form the, do you see what is happening here, is actually the kernel of this homomorphism, because in the space of solutions this is the identity element. If you are adding two solutions, then the 0 function is the identity element. It's like adding functions, real valued functions. So you have the kernel here. So that means according to this result, the set of all inverse images of Bx, in other words, the set of all solutions or the general solution to the differential equation is this coset x pi, where pi is the particular integral. But since our group is additive group, so the set of solutions looks like this, k plus pi. Now k is your complementary function, where you write a general complementary function which is a general solution to the homogeneous equation, and with that you add a particular integral that gives you the general solution because of this result, okay, because that is the entire inverse image. I think I haven't been able to fully rigorously say these parts because I have forgotten the actual thing. I mixed this up with vector spaces and things, but you get the general idea. We will discuss about it more clearly when we study differential equations. Okay, so with this I would like to end the video. If you find any doubt regarding this or regarding any other matter related to the things we are doing, then you are welcome to write in the comment section below. So that will be all for tonight. This is me, Lucifer, from a mathematical room. Have a nice night.